Okay, so welcome to the last day of the 5-day long Joy of Geometry workshop. Uh, it is a satisfying experience for me that there has been consistently a sizable number of students in these 5 days, and some of the students were regular who have attended all the 5 sessions, all the 5 days. I mean, multiple sessions over the 5 days, and I'm particularly grateful for them for being a constant companion to me in this journey. So today I'm going to discuss the last part of this workshop, which is about packing problems and algorithms. But before that, as usual, our schedule is the first session is about recap and doubt clearance. So I'll give a quick summary of what we discussed yesterday. So primarily, we saw the use of the Habermas shifting strategy in the context of a concrete problem, which is called the geometric set cover problem for objects that are unit disks or unit circles, and in the continuous setting when only points are given and the objective is to place minimum number of unit circles to cover all the points. And for that, we saw that the shifting strategy can give us a much better approximation. In fact, it can give us an approximation which is called a PTAS, which is close to the optimal in polynomial time. So I have also shared the reference of that paper, and if you have time, you can look at the paper, although the paper is quite old and it is written in a traditional way. So if you have any questions, you can always write back to me. And if you have any question right now, then you can feel free to ask and we can have a discussion. Or if you have any feedback, comments, anything that you liked or disliked about this workshop, then we can have a constructive discussion about it now. Okay, so I hope that I have been able to at least generate some amount of curiosity about problems which relate to geometry and give you a flavor of what geometry people, computational geometry people think about in their day-to-day life. And uh, how many of you think that I have been able to sort of inculcate that spirit of curiosity and inquiry about geometry in you? So how many of you feel that you feel more curious about geometry, learning about geometry uh, after attending sessions in this workshop? Muted. There's a lot of noise on your side.
So, is it better now?
Yes.
Okay, so I was telling that this fascinated me already, even before this workshop, but this really helped to increase my interest. And we had some fruitful discussions as well, all of us. So, I really liked it.
Okay. Thanks for the feedback. So did you have the experience of working in geometry before? That's what you said.
Not formally, sir. I just looked at a few videos or maybe read up on a few things, but definitely not computational geometry as such.
Okay, so that was the purpose, that if somebody is already well versed with geometry, have spent some time thinking about geometric problems or have done a course on computational geometry, then that person is not the intended audience of this workshop. The intended audience of this workshop is somebody who has some idea about geometry or who has done a course on undergraduate algorithms. And with that understanding, if someone comes, then for that person, there is some value addition that I plan to do. and I'm thankful to you that you said that it has been of help to you. So thanks again. Uh, is there anybody else who wants to share something? All right. So although this was a 5-day workshop, we tried to discuss many topics, but because we tried to discuss too many things, we tried to compress so many things within 5 days. Maybe we did not get a chance to go deeper into topics, so explore more things. So in case you are interested, then you can do one semester long course with us. So in fact, in our department, there is a PhD student, my colleague Rachana, who is running one semester long course on computational geometry. And I have been told that she will keep it uh, not complicated. She will keep it simple and easy to understand. So today Rachana is with us, and she will give you more details about the course that she is offering. So Rachana, it's over to you.
Hey, thank you, Siddharth. Hello, everyone. Yeah, I hope you are enjoying the workshop. And yes, I'm a third year student at IISc. My name is Rachna, and I'm offering a course on computational geometry. There will be around 30 to 35 lectures that I have planned. And let me share my screen so that I can, tell you about the topics that I plan to cover. So I hope my screen is visible.
Yes, we can see it.
So yeah, so this is going to be an introductory course on computational geometry, and by now you know what computational geometry is about, right? So it's basically a subfield of algorithms only, and that is the only prerequisite for this course, right? If you have done an undergrad course on, say, data structures or algorithms, and even if you have not done a full course on algorithms, I can point you to some resources so that you can quickly cover some topics that will be required before you get into this course. And these are the topics I plan to cover. So I think it is not important that I describe them one by one here. But any standard course on computational geometry, those are the topics that I plan to cover. And the schedule will be as follows. There will be 2 lectures every week, every Thursday and Friday. This timing is tentative. We can change it as per the availability of students and as per their convenience also. So right now it is 6 to 7 p.m. And yeah, so that is all I wanted to discuss about the. I mean, if any of you are interested in joining the course, then I'll share a Google link, Google form link on the chat. You can register for the course, and I'll share a link to the flyer as well. Yeah. Yeah, I'd like to thank Siddharth also for letting me introduce my course here. I hope some of you will, I hope to see some of you in my course. Thank you.
Yes, so some of the students have been very regular, and I think they have more interest than others. That's why they could hang on to the workshop for 5 days. So I'm sure that some of you will definitely join your course and learn more about computational geometry and be part of the community.
Yeah.
Thank you, Rachana.
Thank you.
So yeah, so feel free to join this course, and she will share the Google form. And I can say that she's an excellent teacher. So you'll have a much better experience than what you had with this workshop. All right. So let's move to today's topic. So I'll share my screen. So what I realized is that people are more responsive to slides for some reason. I think because the topics are getting complicated progressively. I think on pen and paper, discussing technical things which are more complicated takes more time than the short time that we had. Today I'll keep it short, and I have made slides. So right before I started the workshop today, I mean the session today, I was making slides. So the slides are probably not well baked. So bear with me. So let's start the screen. Let me start sharing. Is the screen visible?
Yes, sir, it is.
Okay, great. Okay, so welcome to the session on packing problems and algorithms. So what comes to your mind when you think about packing? Something like this, right? That you have a set of stuff and there's this limited space where you want to pack your stuff. Let me take the pointer. So in this figure, you can see there's a man who is trying hard to pack his many bags into the back of this vehicle. So you realize that these bags could be placed or could be packed in this vehicle in many different ways, and packing in the most space efficient way is a non-trivial task. So even otherwise, in our day-to-day life, packing is a ubiquitous thing. So let us say you get up from the bed and you have 24 hours with you, and then you have to plan how you want to pack all that you want to achieve, all that you want to do over the period of 24 hours. So whenever there is limited amount of space or limited amount of time and you have to pack multiple things into that domain, then you have to think how you can do it intelligently, right? So in the domain of computational geometry, many questions arise, which are fundamentally about packing some objects into some other objects, right? So packing is one of the most well-studied and most difficult of the problems in the field of computational geometry. There are problems which are open for decades, and people have been trying to solve them, but there was only so much of progress in packing. So another example is tiling. So when you have a floor or a wall and you want to tile it in some particular way, and then you have certain constraints to optimize, then that becomes a non-trivial question. So let's start with a small, simple toy packing problem. So in this figure, I'm showing 5 unit squares. Unit means the side length is 1. And I'm also showing another large square whose length is strictly less than 3. This 2.8 is just a number. If you keep it 2.9, 2.99, that is fine. But it is strictly less than 3. Any number which is less than, and it is not too less. It's definitely not less than 2.8, let us say. So it's some number between 2.8 and 3. So my objective is to place these 5 unit squares within this 2.8 cross 2.8 square such that no two square intersect or overlap. Okay. So can we do that? Is the question clear?
Yes, sir. The question is clear.
Okay. So give it a thought for a couple of minutes maybe. So what is your feeling? Is it doable or it is not doable?
I mean, I tried to put all the squares in a corner, and that definitely would not work because we are left with point 0.8 on
Yes.
both the sides. Maybe we can like put the other approach. Maybe since I put all squares into one corner, maybe I can put all the squares in different corners, and maybe there might be some sort of way to put the fifth square in the middle. Maybe. Like I'm
Like
not too
this?
sure. Oh yeah, no. So this would work. Let's see.
Great. So you have found the solution. This is very nice. So, as he was pointing out, Indranil was pointing out, I think Indranil was pointing out, that if you put 4 squares at the corners, then you must tilt the fifth square. The fifth square cannot be placed in vertical uh, orientation because vertically only 0.8 distance is left, space is left. Horizontally also only 0.8 space is left. So, but you can tilt it because the diagonal distance between this point and this point, that is more than 1, right? So everybody convinced we can do that? So the question is that what is the limit? What is the smallest large square that we can think of for which we can do this packing of 5 unit squares? So if the large square is shrunk progressively, then a point will come when this central space, this central unoccupied space, this empty space will become insufficient for this fifth square to be accommodated. So maybe you can give it some thought. The smallest large square in which 5 unit squares can be packed. So I want to know that what is the side length of the unit square for which we can achieve this packing.
So is it 2 plus 1 by root 2?
Yes, it's very nice. I really appreciate it that you found. So it's with some playing around. You can see that if you uh, make this fifth square touch this bottom right corner of square 1 and top left corner of square 4, then you can do the calculation by using Pythagoras theorem. And I think that's what Indranil has done. It's very nice. It's a good job. So that turns out to be something like 2.707. And there is a proof that one can do better. So smaller than this distance, smaller than this dimension of the square will not be able to accommodate 5 unit squares. So this is just to warm you up. Now let's look at a more complicated question. Or rather, this is the uh, gearing up for that more complicated question. So here I allow the size of the square to vary. Okay, so I'm saying that there are a couple of squares, but the squares need not be of the same size. So in this case, in this toy case, it is the same size. So in this case, we have 2 unit squares again. The side length is 1 and area is also 1. So what is the total area of these 2 unit squares? That's 2. So I want to ask that can we pack them non-overlappingly into a square of area less than 2 times the sum of the areas. That is so 2 times, so 2 times the sum of the areas is 4. So if the side length is less than root 4, that is less than 2, then we have a square like this. Okay, so this is the larger square. Let us say its square side length is 1.95. So the question is, can we pack 2 unit squares non-overlappingly into this square? Even 1.99 is allowed, but it's strictly less than 2. The side length is strictly less than 2. So that the area of this larger square is strictly less than 4. So what do you think? Is it doable?
Sir, if we suppose our approach be that we don't tilt the squares, we just place it as you have placed, and maybe another square either on top or on the right top.
Yes.
And if the square sides are x and y, so we have x square plus y square equals a, and we want to find out if this is the case, then can x plus y be less than 2a? So this is what we
Oh,
need to figure out, right?
no, for now, there is only x, means both the squares are of equal length.
Oh, okay.
I mean, in this toy example, we have both the squares as side length 1 squares. So overall area is 2.
Okay.
So you have 2 squares, equal length squares. Let me also write this thing here. This is also side length 1. And I'm asking a very specific questions whether these two unit squares are accommodable within this large square.
Yeah, I don't think so.
Right, so this is not possible. And why it is not possible is that once you have placed the first square, and let us say you do it greedily, you place it at one of the corners, then this the white space that is left for you. I mean, so let me put it this way. So once you have placed, sorry. What did we take? Oh, I should have taken the eraser. All right. Right. So once you have placed the first square in this way, adjoining one of the corners of the larger square, then you are left with this empty space, which is L-shaped. Okay. Now, this L shape is can be thought of as being formed of two overlapping rectangles. Okay, so let's put it this way. So this L shape can be thought of as two overlapping rectangles, such that this part, which is the part common to the two overlapping rectangles, this part. So this is also a square. So its dimension is only 0.95. And that means the other square, if you tilt, if you bring the other square and if you tilt, then this space will not be sufficient to accommodate it. On the other hand, if you don't tilt, then you don't have sufficient y distance to place the other square. You have only 0.95 y distance, whereas you want 1 distance. Similarly, here also you have only 0.95 x distance, which is not sufficient to accommodate the other square. So if you have such kind of a square, 1.95 side length, then you cannot ensure that two unit side length squares can be packed into this large square non-overlappingly. But see, once you increase 1.95 to 2, then it is trivial. Then you can place the two unit squares side by side and the packing is complete in non-overlapping way. Okay. So therefore, with this observation in hand, we'll ask a more general question. So the answer is no. We cannot pack non-overlappingly two squares into this larger square having side length root 2 minus epsilon. Now, here is the general question. In this question, you are given n variable size squares, and the sum of the areas of the squares. So let us say that side length of the first square is a sub 1, side length of the second square is a sub 2, and so on. So the sum of the areas of the squares is denoted by capital A. And now you're given this larger square whose area is 2 times capital A. And because it's a square, its side length is root over 2A. Now, the question is, we have seen for the toy problem that we could pack the 2 unit squares into a square of side length 2. But in general, when the squares are variable sized, can we still pack them non-overlappingly into this square whose area is 2A? All right. Is the question clear?
Yes, sir, it is.
So what should we do? Previous slide only is better, but I didn't have. Okay. So think of it this way that, okay, I want to achieve this. So I want to propose a packing algorithm. And then after the packing is done, then I want to prove that none of the squares is protruding outside of the box. So first step is to sort of design an algorithm that places these squares into the box non-overlappingly, and then argue that there is no square that violates the boundary of the large square. So there is no square after packing all the squares non-overlappingly that moves through the boundary of the larger square. The first step is to come up with an algorithm, and the second step is to argue that there is no violation of the boundary of the larger square. It's the most natural strategy.
So maybe start off with the smaller squares and among them which one has the largest area and basically a greedy approach
Okay,
and try placing them.
makes sense. So what is the greedy rule you are suggesting?
Sir, the area of the smaller squares, the maximum area.
Okay, so you start with the largest square and you place it into one of the corners. That's what you're saying.
Yes, sir.
All right. Okay. How did you know this? I am going to do exactly the same thing. So first step is to sort the squares in decreasing order of size. Okay. And then we'll place the squares in that order, decreasing order of size. So first let us sort. Great. We have put the squares in sorted order. And now we will have to decide that how we are going to place the squares within the large square. So what is the most natural way to place? Shall we place it at some corner or shall we place it randomly anywhere within the large square? Better to place in the corner. It's my pointer. Let's take the pen. Our pen is already taken. So let us say I place the largest square adjoining the bottom left corner. And then I have the next square. I place it adjacent to it. And then I have the next square. I place it adjacent to it. And then I have the next square. I try to place it adjacent to it, but then I realize that I'm violating the borders, which I'm not allowed to do. Then I say, no, I must stop here. So I take the eraser. So I decide against doing that. So what do I do next? So greedily speaking, we can place the next square so that it is stacked up on one of these three squares. So which out of these three squares should I stack the next square on?
Sir, maybe the smallest one because that small space we are left at the right end won't be used anywhere.
Yeah, that space is sort of unused and that space is sort of wasted. So this space is sort of wasted and we have no hope of using it, reusing it in the future. So I'm fine with it because see, what is the total area of the squares that I have? So all the squares taken together is area A only. This is area A only. And on the other hand, what is the area of the square? Larger square. The area of the larger square is 2 times A. So I can afford to waste at most A area. So I have enough room to breathe. So some space is lost, I don't really care, but I have to be able to argue that the empty space is not too much. But you are right. That why don't we put the next square here? And then what shall we do? Where does the next one go?
Sir, I was thinking maybe like even put it towards the right, like more right, above
Okay,
the empty space.
okay, so it's touching the right boundary of the larger square.
Yes, sir.
You want to place it somewhere here like this. So no space is wasted except the yellow marked space. So what do you do next? The next one comes and then what happens to the next one? Does it so the next one touches which one? So suppose the next one is sort of, if you want to place it next to this guy, it sort of overlaps with the second square that we have put, this guy. This is second square, this is the first square, this is the third square, and now this is the fourth square. And it is very well possible that the fifth square can sort of overlap with square 2.
Okay, then instead of going left, right, like from right to left, like initially, like we went rightwards. So after we're done rightwards, maybe we move up from the bigger square, maybe.
Very
Right.
nice. With that strategy, what you suggested, we will not get into such complications. So see, since we have the liberty to waste half of the space, then such complications will only hinder our ability to argue. So let's not get into such complications. Let's take the fourth square and let's put it on top of the first square. And now when the next guy comes, I sort of be more generous and can I draw a straight line? Okay, so I will try to draw a straight line freehand. Okay, it's not looking good. Suppose this is a straight line. So I take the liberty to draw a straight line, which is containing the top side of the first square. And as such, I also give up this space. So I also lose this space. And then I say that, look, now I have a similar kind of setup. I have, instead of a larger square, I have a rectangle. And on top of this rectangle, I mean, within this rectangle, I will place the rest of the squares that will come. And I do that. And then at some point we will again have this issue that the next square is sort of going to violate the boundary of the enclosing, and then we will repeat the process. So this is well defined. You understand the process.
Yes.
Okay. So now what are we left to do? So we are left to do what we are left to do is we have to argue that how much space is lost, whether we have more occupied space or we have more empty space. Okay. No, I mean, that's not that way. It's whether we have violated. Oh, that's fine. So if we are able to put every square inside, then exactly A space will occupy. So exactly A space will be empty. So better way to put it is that whether we have violated any of the boundaries. So if we keep on doing it, so what we have to check to test whether there is a violation is what is the last square in the first column. So you have to check the height of the first column. So if the height of the first column is more than root A, then we have violated. Otherwise not, isn't it?
More than root 2A, I guess.
So what did I say?
I said root A.
Oh, no, sorry. Yeah, you're right. So the height of the enclosing square is also root A, and we don't want to have a column of squares that is more than root 2A. So is there any other possibility in which we can violate? I mean, if we violate the boundary, this is definitely bound to happen. I mean, maybe there are other violations, but this violation will come first before anything else. Do you agree?
Yes.
Now it is difficult to argue. So people realize that it is difficult to argue this strategy, that whether there's a violation or not with this strategy. So people became more generous. So people realize that we have to be more liberal in giving up space. So they slightly tweaked the algorithm. So what they did is the following. So they said, okay, the first layer is formed. So once the first layer is formed, then the square that is not accommodable within the first horizontal layer, that you are putting it on top of this first layer, that is fine. But the second square of the second layer, don't put it adjoining to this first square. You also draw one more vertical line. So we have drawn this vertical line. So with respect to the first square, we have drawn one horizontal line, which is containing the top boundary of this first square. So they're saying that, okay, you also draw another line, which is containing the right boundary of this first square that you have put. Okay. So now I'll delete the previous backing. So I'll delete these guys.
I think switching to whiteboards will help.
Is this not understood?
Yes, but it will be good, I think, switching to whiteboard.
Yeah, so I'm not going to do a lot of handwriting. Maybe just another minute, then we will have many slides. If still, if the algorithm is not clear, we can go to the whiteboard. You are right. So what we have done is, I'll repeat what I said. So I put the first square, the second square, third square, and then we realize that in this layer we cannot put another square. So we said, okay, I'm going to draw a horizontal line, which is passing through the top side of my first square, and also a vertical line, which is passing through the right side of my first square. And now I am going to place the rest of the squares to the right of this boundary, this vertical line, and above this horizontal line. That is the algorithm. The next layer will come like this. Next layer will come like this. And then we realize that, okay, we cannot move it further. Then we have the next layer, next vertical layer. I mean horizontal layers. Sorry. So next guy will, oops. So next guy comes like that. Okay. Oh, this is larger. Let's make it smaller. Kostav is right that it's better to do these things in the whiteboard, but in the interest of time, switching to whiteboard and coming back, that takes a lot of time because there are more slides. So now I have this guy, and I also put another horizontal line, and then the next layer sort of is adjoining this horizontal line, and so on. So if the algorithm is not clear, we will go to whiteboard. What do you say, Kostav?
Yes, yes, the explanation is like I was able to follow.
All right, great. Is there anybody who could not follow the algorithm? So let's see. So we place them generously in layers. So this is what happens. So this is what happens. So we had this setup. So 2, 5, 1 could be accommodated within the first layer. And then 4 and so many things could be accommodated in the second layer. Maybe there are more layers. Okay. Now we shall argue that the height of this first column that is less than root 2a. So how shall we do that? Okay, now there is some notation. So let us say, so the side length of the first square is a1. The side length of the second square is a2, and so on in the decreasing order. Okay. So therefore, area is this summation of the AI squares. And let us also give special names to these squares which are forming the first column of squares. So the first square is also called, I mean not called, it has side length a j sub 1. So this guy, that is the first square in the second layer, it has side length aj2 and so on. So the height of this column is, let us say there are k layers. Say there are k layers. Then the height of the column is summation of a sub j I from 1 to k. Is that fine? So whether this statement is fine.
Yes, it's fine.
All right. So now let me, I could not finish making the slide. So these things could have been put on the slide. So let's do it on the slide. So I am saying that. So this. So how I should put it? Let's take a thing. So we have to define one more thing, which is called W. Oh, this I have not copied. This slide is better. Let's do one thing. I'll copy this this guy. Put it here. Let's just give me 2-3 minutes. So this this width of the rest of the squares in layer 1, I'm going to call it W1. Okay. So this width, I'm going to call it W1. It's small as me. Okay, so let's do the things we can define analogously. So this width is W1. Now in the second layer, this width is called W2. Making slides is very time taking. So all good. Let me also so the ages. So ages I already described, but let me also say it here also. So the first square of every layer, that guy is being denoted as A sub J sub I. So this guy is AJ1. Okay, and the next guy is AJ2 and so on. Now I think we can describe what we have. Yeah, I think let's see. Okay, so this figure we can ignore. Yeah, let's do the slideshow once again. Okay, let's look at the notation once again. So in the first horizontal layer, the first square is denoted as AJ1, and the width of the rest of the squares is W1. In the second horizontal layer, the first square is denoted as AJ2. I mean, the side length, the side length of the first square is denoted as A sub J2, and the width of the rest of the squares in this layer is W2. Now we can see this equation. So what is the height? Oh, H. I should also write H. Okay, so let's also write H. So the height of the first column is h.
Your presentation is stopped.
Presentation is stopped.
Yes, yes. I'm
Yes,
not able to see the
we
presentation.
can't see.
Let me check. You can hear me.
Yes, yes. You're audible,
Yes.
but your screen presentation is stopped.
Okay, then it's not an issue of connectivity. Let's see what is the problem. Change spoken language. I don't know. Change on message. Sir, I got temporarily disconnected. May I please repeat the question? Show him the 535. If you ask that question in voice, in audio, then I can repeat because I'm not checking the chat. So when I'm presenting, I cannot see the chat. So Shubham, are you still there? You can unmute yourself and ask the confusion. All right, I think Shubham is not there. Anyhow, let's go to sharing the screen once again. I hope the screen is visible now.
Yes, it is visible now.
All right, so let's go back to the slideshow from current slides. So we want to, what do we want to argue? We want to argue that the height of the first column in our backing, which is h, is strictly less than root 2a. I mean, we will allow root 2a equality also. Yeah, I mean, let us say we want to prove that h is at most root 2a. Then we will be done. Okay, so now we have all the notation in place. So in the first horizontal layer, in our packing, which is given by our algorithm, the side length of the first square we denote it by a sub j1, and the width of the rest of the squares we denote it by w sub 1. Similarly, in the second horizontal layer, the side length of the first square is denoted by a sub j2, and the width of the rest of the squares is denoted by w2, and so on. And let us say there are k layers. K layers. In this case, there are only 2 layers, but in general, it will say k layers. Then the height is this quantity. Are you with me?
Yes.
Yes.
Okay. Now I said that A is the total area of the squares. Then you can write A as the sum of A squares, because A sub I is the side length of the ith square. So that is how we have this equation. Okay. So now observe what we are doing in this step. So we are saying that taken out the first square's area to the left hand side of this equality. Now we are giving a lower bound on the area of the rest of the squares. So first focus on these 2 squares. I mean the rest of the squares in layer 1. So if you multiply W1, that is the total width of the rest of the squares in this layer, with the height of this square, which is AJ2, then that is the lower bound on the total area of these squares, because this square is anyway smaller than any square here. So W1 times AJ2 is the lower bound on the total sum of the squares here. Similarly, what is the sum of the square? What is the sum of the areas of these squares? So forget this square for now. I'm only interested in the lower bound. So this width 2 times whatever is here, aj3. So that is what I'm writing, and so on. Do you understand?
Yes.
Yes.
Okay. Now, one more interesting thing. So W1, or for that matter, W2, or any W sub I, it cannot be more than this part, which is root 2a minus a1. A1, this square is the first square. Its side length is a sub 1. Also, a sub 1 is equivalent to a sub j1. So this part is the entire thing, which is root 2a minus a1. So this is an upper bound on every wi. Did you say the right thing? So do you understand? I said in the last step, I said something incorrect. So do you see that there is a problem here?
I think it is at most.
No. So let's recap what I said. So let us understand this thing. What is W1? So W1 is wrong, not as in this figure. So W1 is the width of all the remaining squares plus the width of this guy. So I have to put it this way. So now I realized it. So otherwise the argument will not go through. I'm sorry for the hiccup, but I can't help it. So the next square, if we had put the next square, which would have violated the boundary, that square taken together, the total sum is W1. So there is a violation. This will lead to violation. Okay, in the last layer, there is no violation. Don't worry about it. Yeah, so this is fine. Okay, so let's understand what is W1. So W1 is the width of the remaining squares in the last layer plus the width of the next layer's first square. And W2, because it has ended, that is why. So there are no squares beyond this. So W2 is ending here. But I mean to say that at any intermediate layer, W sub I is the width of all the remaining rectangles, barring the first rectangle square. The width of the total width of the remaining squares, barring the first square, plus the width of the next square. Okay, so now this argument goes through. Okay, so now why does this argument go through? So consider the area of the remaining squares in the first layer plus the area of the, let me take a pointer. So let us understand one layer. If I understand one layer, we can understand one layer, the rest of the layers will be clear. Consider the area of the remaining squares in first layer plus the area of the first square in the second layer. This is at least this width one into the height of this square. But this width, every wi, is at least root 2a minus a1, except probably in the last layer. Is this convincing?
I have a doubt. So let's say W2 is the width of the last layer, like kth layer. So can we expand WK to span the entire, like up to the boundary of the larger square of side length root 2A?
Let me understand what you were asking. So you are considering the last horizontal layer, that is the
Yes,
kth layer.
yes.
And in kth layer, we have not. So in kth layer, WK is not going beyond the boundary. And then you were asking, what is the question?
No, I was asking that we can expand WK to reach the boundary of the larger square
Okay, let's
because
do
we
that.
are finding the lower bound.
In this figure, let's do that. It is okay. So you were asking whether this is possible or not. That's what you were asking.
I think in this case only, like the inequality holds.
So you think the other steps, the inequality does not hold?
There can be cases where like all the Wi's go up to the boundary only. Because the Wi depends on the length of the square.
Okay, so let's try to do this once again. So we want to get a lower bound on this quantity. So what we said is that we will look at this sum into parts. We look at this sum in parts. So we say that okay, one part is this remaining squares plus this square. And then we said that okay, this is at least W1 times this height. So it is W1 AJ2. And then we went to the next layer. And then we said that okay, these squares and if there is anything, this together is at least W2 times the height here. But all this thing will go through except at the last layer, isn't it?
But you like I iterates from 2 to k, right? You are going up to kth layer.
Yes. Oh yeah, we are going up to kth layer only. So this should go through for all cases, right?
Yes.
Oh, little. So you have helped me understand this. So I can understand the truth of this statement now. Are you also convinced?
Yes.
So let's write one more thing. So I think we got confused because the slides were not ready. Let's write one more thing. This will make everything clear. That for every I, W sub I is at least this. Okay, let's make it equation. This one statement is also necessary. So the width that every layer is greater than equal to root 2a minus this a1. So I will write root 2a minus a1, and I'll make it larger. So for first layer, W1 is going beyond, is violating the boundary. So W1 is more than root 2a minus a1. That is true. And I am going till k clear only. So the last layer is not necessary. That's what Kosov has pointed out, because when the last guy, if there is anything at all, let us say this picture is not self-explanatory. Let us say there were other squares here, and then there was a last square. So I am going to check uh, the sum of the areas of these squares, and I will say that is at least this guy times this. So I don't have to check the width of the last guy. So WK will not count. So till WK minus 1 only I have to check. Okay, so what? Yeah, so because every WI starting from 2 to k minus 1 is greater than, I should take from 1 to k minus 1. Just a second. I'm meeting actually. So W1 is to be taken. That is the reason. What am I doing? This was okay only. W move. So I moves from 2 to j. Means W moves from 1 to k minus 1 only, right? Okay, so let's do it once again. So what this is saying is that you start from I equals 2. So there's AJ2 and you move to K. So there's AJK. When you are looking at AJK, what is your W's index? W's index is 1 less. So W is till K minus 1 only. So such a situation will not prevent us from concluding this lower bound. So, is that right?
Yes, 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 yes.
Is there anybody who has an issue? I mean, who has a doubt? We can talk about it. So I think it was all right, but I confused myself. So anyway, I'll share the slides so you can also take a look at it later. But what this lets us prove, okay, so what is the height of this column? So this is aj1 plus all this other heights together, that is upper bounded by a minus a1 square divided by this quantity. So a minus a1 square. So height is aj1 plus all these things, aj2 plus aj3 and so on. But this quantity is at most this thing a minus a1 square divided by this quantity. So that's what I have written. And then we can simplify this. So aj1 is nothing but a1. So this quantity is at most root 2a because of this inequality. A minus b whole square is greater than 0. So you can look at it and convince yourselves. If any of these steps is not clear, then we can discuss about it. So basically, if you simplify this, and then if you take these things, all these things to one side, then you will get this inequality. So a minus b whole square is greater than 0 anyway. So that is why this thing is true. So that's how the height is at most root 2a. And that's how we have proved what is called the Mohn-Moser theorem. And it says that every set of squares of total area 1 can be packed into a square of area 2. Furthermore, this assertion is false if 2 is replaced by a smaller constant. So we have seen in the beginning that if the square size is strictly less than 2, then 2 unit squares cannot be packed into that square. But if it is twice the total area of the squares, then we can do that with this algorithm. So thank you for attending. And so yeah, we had some feedback before. If you have any comments or feedback, anything you didn't like, you liked about this workshop, we can talk about it. And this is going to be the last session. So this is sort of the end of the workshop.
Can you please go to the previous slide?
Yes.
So in the theorem statement, every set of squares of total area 1 can be packed into a square of area 2.
Yes.
Like 2 times the sum of the
Yes.
areas of the squares.
Yes.
Okay.
But if it is less than 2 times, then there could be cases where this packing will not be possible.
So
Is there anybody who has a question or anything to share?
Sir, it will be helpful if you please share some reference materials too.
Yes, I'll update the website and I'll share the updated website with the links with all of you. I did not get time. I will do it in 1 or 2 days.
Okay, thank you.
So I'll send you a mail, all of you. I'll send a mail, and in that mail, I'll. So first of all, thanks all of you once again for joining the workshop, and it has been a learning experience for me as well. And I'd like to thank all the people who have helped me do the outreach, spread the word. I have written to a couple of professors in IITs, uh, including Professor Palash Sarutam from IIT Kharagpur and Professor Subramanian Kallamasundram from IIT Hyderabad, Professor Gautam Das and Professor Inguli from IIT Guwahati, and a couple of others. So for that, but yeah, all these profs, they have helped me reach out to many of you. So thanks a lot. And we'll keep in touch. So I'll send a mail and you can always keep in touch with me by sending me an email. I generally check my email regularly. So thanks a lot for coming. So this is the end of this workshop. Thank you.
Thank you, sir.
Thank you, Siddharth.
Thank you.